All right. Okay. Good morning. Hope you guys are doing well. Um, and we'll get started. Okay. So today, I thought we would take a look at. I've uploaded a few links on CCLE, and I thought we would take a look at the MNIST handwritten digits database. Okay. And so this is the official MNIST database. If you go online and you search for MNIST database, there's several, there's several things out there. Um, but um, but this is the official one. It comes in this kind of slight uncommon file format, but you're going to download that somewhere onto your computer and unzip and untar all of these things into your directory here. Okay, and so when you do that, you're going to have these files, and then you can load them into the computer, and I'll show you, or into R, and I'll show you how to do that. So so if you want to follow along, you don't have to, but you would download kind of these 4 files, and then you'd have to I guess un-GZ them. That's the storage format into a directory that you would title MNIST. And then once you do that, I put in a couple scripts here. One is to load the data, and then the other is what we're going to use to create and train our neural network here. So so the script to load the data looks like this, and you are just gonna so this is the script to load the data. You're gonna just kind of load that into R, and then there's basically 2 functions. One is load MNIST, and then the other is show digit. And so here we can call the function load MNIST. I've already done this, and so in my environment, I already have the train and test kind of data sets, and they are loaded in memory here. Okay, and with that, we can then start to take a look at some of the elements in there. Okay, so if I do this, let's just say we do it kind of for the first element. Okay, so I'll do j equals 1, and then we're going to take a look. The label, the answer that this is supposed to be, is that it's the number 5, and then the digit itself is stored as a vector of 784 values. Okay, 784 values ranging from 0 to 255. Okay, 0 if it's if there was nothing written there, up to 255 if something is written there. Okay, and if I click show digit, this is the plot of the digit. Okay, so you know, the researchers, when they created this data set, they scanned a whole bunch of handwritten digits, and then they cropped them into tiny little squares of 28 by 28 pixels, and digitized all of them. And they did this for thousands of digits, on the like 60,000 digits. So it's a lot. Okay. And what we're going to do is we are going to create a neural network that is going to take this input of 784 values, okay, and then so there's no real structure to this this data set, okay? Or not the, I shouldn't say data set, but it's just one string of 784 values, and we're going to put that into the neural network. And hopefully what we want is the neural network to go through and produce a prediction. We're going to just use our very simple one hidden layer design, okay? Which is, we went through on last Friday, and on Monday, we went through the kind of the back propagation rules for figuring out the gradients, and we're going to use that to, we're going to use gradient descent to train it, okay? Let me just show you some of the other digits, what they look like. So here's just another value. So this is the digit 0, okay? So we can see the label on this is 0. The label on the next value is 4, and that's what it looks like. And here's the label 9, okay? Let me just pull up the chat, make sure, see if anyone's asking questions. Okay, so so that's what we've got going on. And this is an old slide that I want to kind of show, but you know what? The 3 blue, 1 brown has a important or has a good diagram of what happens. Okay, so I'm going to go ahead and play this clip of his video.
Typically a number between 0 and 1. It's really not more than that. For example, the network.
So he talks about, so right now my data is going from 0 to 255, and we can scale that digit, those numbers, so that they, if I divide by 255, then it will change everything to be on a scale from 0 to 1. Okay, so so we'll have that as far as our data goes. Okay, and so here's kind of what this is the image that I have in my data set. So this is, so he's using the same database that I'm using. Okay, and this is 28 by 28 pixels, and he's going to illustrate.
Work starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these.
Can you guys hear the audio from the video? I hope.
Yep.
Oh, okay, great. Okay.
Holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels.
Okay, and it's just the opposite on my image. It's 0 for white and 1 for black.
This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network.
I just love that animation of showing how all the pixels, get lined up, basically turned into just this vector of 784 values, and so that's what we have. And basically, so he builds a more complicated neural network. Okay, so he has several hidden layers. Just for our sake, we're going to keep it simple. We're going to have the input layer, just one hidden layer. So he's got a couple hidden layers, and then we're going to have an output layer. Okay, so he has 2 hidden layers, but
now jumping over to the.
But we're just going to have one. Okay, just to kind of keep things simple. All right, so we're going to have just one weight matrix from the hidden layer to the output layer, and then another weight matrix from the input layer to the hidden layer. And again, every kind of node is connected to all the nodes in the next layer.
The last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit.
Okay, and that's what we're going to have. In the output layer, we're going to have 10 neurons, okay? and they're going to correspond to the digits 0 through 9. And basically what we're going to do is for this training image, we're going to tell that the target, what the neural network should target is all of these values will be 0, and then just this one should be a 1. Okay, that's what we're going to target there. Okay, and now and that's going to be how we set up our training data. Okay, so there's a reason why we need to have 0 through 9, because in the other when we were doing the hours of sleep and the hours of study predicting the test score, there was only one value to predict, and that was the test score. And you might say, well, why don't I just predict the value of the digit? Okay, why don't I just predict 0 if it's 0 and 9 if it's 9, or 3 if it's 3, or something like that? There's a reason for that. Okay, when you have, if you only have one digit, okay, if you only have one digit, then you have varying degrees of how right or wrong you are, right? So let's say the correct value is 9, and if you only have one digit or one node, okay, and the correct value is 9, and you predict that the value is 8, we'd say, oh, you're not right, but you got pretty close. And if you predicted it was a 1, you're like way off, right? 1 or 0 is more wrong than predicting 8. Okay, the correct answer is 9. But as far as if you use one node, it's kind of a regression problem, and how wrong you are is going to vary, or is going to be different based on how close your number is to the real number. Now, as far as digit categorization though goes, or classification, that's not how it works. If the correct answer is a 9 and you predict that it's an 8, that is equally wrong as if the correct number is 9 and you predict it as a 1. Okay, so even though these are numbers, we're predicting digits. You either predicted the correct digit or you did not. Okay, we don't want to tell our system that, predicting 8 is a better guess than predicting 1. Okay, we want to say 8 is wrong, 1 is wrong. Anything other than 9 is completely wrong. Okay, there's no varying degrees of correctness. You either predicted the correct number or you didn't. Okay, whereas if you used a single node like regression, then we would say, hey, we want you to get close, and the closer you are, that's better. So 8 is not as bad as is better than predicting 5, is better than predicting 1. We don't want a system like that. Okay, so that's why we're going to have 10 different nodes, one for each digit. Okay, I hope you guys watched this video. We're not gonna spend much more time on this video itself. So, but it's got some beautiful animations in there, and Grant is he's very good at explaining these things. He's also holding these live streaming sessions. You should subscribe to his channel, and he's holding these live streaming sessions on kind of like math that you probably learned in high school and stuff, but it's he does a really great job of explaining those things. So anyway, I recommend his channel. Okay, so let's go through this code here. Let me I'm gonna just go ahead and make my code a little bit bigger for you guys, and you guys probably can see just fine. But okay, so I've gone ahead and I've loaded up the data. Okay, and so this is a function that is going to turn our label, okay, into a vectorized label. Okay, so let me just kind of show you what it does. Is I'm going to apply this vectorized function, and basically it takes it creates a vector of 10 zeros, and then to the correct label, it's going to change it to a 1. Okay, so I'm going to go ahead and run that. And so, so when the value is 5, the first row, it's going to put a 1 for the node that corresponds to 5. Okay, so so the nodes go, this corresponds to a 0, and this one corresponds to a 9 over here. And so this one will be a 5. And then the next value, which is a 0, it gets a 1 in the second row. There's a 1 for the 0 node, and it zeros everywhere else. The next value is a 4, and it's basically zeros in all nodes except the one node that represents the digit 4. Okay, so this is we're going to tell our system these are the target values. For the first observation, you want to get all zeros and you want a 1 here. For the second observation, you want a 1 here, and everything else you want zeros. Okay, that's what we're going to tell it. Okay, and so I think this just plots that digit. Okay, and a lot of this comes kind of straight from the notes that that I had on Monday. Okay, on Monday I think I had all of this coded up here. So we're going to code up our sigmoid function, our sigmoid prime function. Here is the cost function. Okay, and the cost is going to be the sum of the differences between our predicted. There's 10 nodes to predict. We're going to take kind of the difference there, right? And so, so here for my network, I've got 784 nodes in the input layer, and that's the 28 by 28 pixels. And then for the output layer, we have 10 nodes, okay? One for digits 0 through 9. And then for the hidden layer, I've chosen 30 nodes. That's just kind of arbitrarily chosen. And I'm choosing just to have one hidden layer to kind of keep things simple. You know, in this video, he's got kind of 2 hidden layers, each with, I don't know, looks like 15 nodes or something like that. Or 16 nodes, I don't know. But yeah, I just have one hidden layer of 30 nodes, okay? All right, so to train this, I'm going to start off with some random values for my weight matrix. Okay, so I've got 2 weight matrices. I've got you know, weight matrix between the input layer and the hidden layer. That's weight matrix 1. And then we've got weight matrix 2, which goes from the hidden layer to the output layer. Right? Let's see. I think I've got, yeah, this is exactly what we've got going on. All right. So so the next thing that that I'm going to code up here is what we call stochastic gradient descent. And the way stochastic gradient descent is going to work is that I've got 60,000 entries in my training data, and it would bring my computer to its knees to try to do the computation for all 60,000 images all at once. Okay, so we're going to break up the data into smaller batches. Okay, we're going to have 6,000 batches of 10. Okay, so because when you find the gradient, okay, it takes kind of your data, and it says, you know, this is kind of the calculations for the gradient involve you know, several the predictions and whatnot, and so, you know, I would have these giant matrices, you know, n by 784, so I would have 60,000 by 784, which would be incredibly huge. So instead of that, I'm going to break it down into small batches of 10. Okay, and that's going to allow my computer to kind of progress through the data a little bit faster, or not, I wouldn't say faster, but allow it to kind of just be able to handle an iteration. And so so I'm going to split up the data into batches of 10, and then I'm going to kind of cycle through. So we're going to take 10 random images, do one iteration of calculating the gradient. And so we find the gradient and we take a step using gradient descent using 10 images, okay? And so, and then for the next step, we're going to use 10 different images, okay? We're going to go through the next iteration. We're going to use 10 different images to calculate the gradient and take a step there. And we're going to take 10 different images in the next step and calculate the gradient and take a step there, okay? So, you know, using in gradient descent, we use kind of our data to figure out which way is pointing up or down, and we take a step down the hill. And the reason why I want to split this up is if I take all of the data all at once, it's going to overwhelm the system, or it's just going to be very computationally expensive. And so I split it up, and basically you're getting kind of like an approximate answer. You're hoping that these 10 images you've selected are kind of representative of the digits that count. Okay, so so I'm going to go ahead and do this, and you know, we have 60,000 of these images, and I've just kind of arbitrarily chosen a learning rate of 1, and this part is the gradient descent. Okay, so so let me just show you what J sub. This is basically a vector that counts by tens. It goes 1, 11, 21, 31, 41, so on and so forth. Okay, and then and it's going to select the rows. The rows it's going to select is it's going to take so it shuffles the indices 1 through 60,000. Okay, and it's going to just go from 1 to, and it says basically 10. Okay, so for the first iteration, it's going to start at I, and it's going to end up at I plus the batch size is 10. So it's going to go to 10. This is I plus batch size minus 1. So that's going to be 1 through 10. Okay, and then at the next iteration, I is going to take on 11. Okay, and it's going to go from 11 to 11 plus 10, which is 21 minus 1, so 20. So the next iteration is going to go from 11 to 20. Okay, and then the following iteration, it'll go from 21 to 30, and then the following iteration, it'll go from 31 to 40, so on and so forth. So it'll split our data up into batches of 10 at a time. Okay, and so we subset our full training data, okay, the X matrix in our training data. We're going to subset it just to those 10 rows. And then and we're going to divide everything by 255 so that all the values are on a scale from 0 to 1. Okay, so so our data goes from 0 to 1, and we have 10 rows. So X is going to be a 10 by 784 matrix. Okay, we've got 10 rows, 784 columns in X. All right, and then the output will be our Y matrix. Okay, and now that we've turned our labels into 10 columns, 0 through 9, Y is going to be a 10 by 10 matrix. Okay, so let me just show you. So if I've got I equals 1, just to kind of illustrate this, all right, then so the rows, these are the 10 rows that I've arbitrarily selected, and an X, well, I'll just show you the dimensions of X. Dimensions of X will be 10 by 784, and then Y will be, the dimensions of Y will be 10 by 10. Okay. And and then we create our predictions using our current, which are totally random values for our weight matrices 1 and 2. So we use forward feed. So we do x times w1, sigmoid of z2, a2 times w2, and sigmoid of z3. So this is just the forward feed part, and this will create our this network. I'm going to just kind of forward feed. And so my y-hat predictions, so let's just show you the first row, okay? These are absolutely terrible predictions, okay? As we would expect, okay? They're absolutely terrible because I just have random weights going in for weight 1 and weight 2, okay? And so, you know, these are my predictions ideally for this image, this first image, which is 24388. What is the image? Oh, okay, it happens to be a 9. Okay, so we want we want this y-hat to be for this row, we want it to be all zeros or values very close to 0, and this one to be a 1. Okay, that's what we want. Okay, that's not what we have. We just have totally random values here. And so we're going to calculate basically the gradient here. Okay, so we're going to say, all right, and this is what we calculated on Monday, okay, using kind of our back propagation. So we calculate the gradient with respect to the W2 matrix. We calculate the gradient with respect to the W1 matrix. And then we do the gradient descent. So we take our current values of W and we subtract off a scalar times the gradient. Okay, and this will, we hope, okay, so sorry, this has kind of our predictions here, and or not predictions, our weight matrix. Okay, and ideally what we want to see is, so this is using the old weights, is that if I were to make new predictions, what we're hoping is that after applying the gradient, okay, I can't tell what happened, but the idea we're hoping is that after applying the gradient and taking a step in the kind of the correct direction, that that we would get closer to the output where these are all zeros and this is closer to 9. It doesn't look like that happened here, but anyway, I'm going to go ahead and I'm going to just apply that. So let me just kind of run through all of this. And we're going to do that for using all of our batches. I guess I should pause here and just check and make sure everyone is doing okay. So give me a green check mark if this is all making sense, what's happening, and then or give me a red X or raise your hand or something if you have a question. Okay. And then let me give you the first quiz answer. The first quiz answer for today is E as in elephant. E as in elephant is our first quiz answer here. Oh yeah, I've yeah, okay, sorry. I've toggled the chat so that your chat allows you to chat to the public room. I made it private yesterday for, or not yesterday, on Wednesday for the exam, but now it should be now you should be able to chat. Okay. The first one's always that's I guess that's what it's been this week. You know, when I selected the answers, I just had R. I literally had R do a random sample for me, so I didn't arbitrarily do these answers here. Okay. So where did I go? Okay, so now we're going to go ahead and apply the batch gradient descent. I hope this works. It worked. I tested it out earlier and it worked. So I hope it works today. Every time you do something live, sometimes things break. Okay, so it'll take a couple seconds to run. So it's running, and it's going through all 60,000 images, and it's done. Okay, so I just did one iteration of well, I did 6,000 iterations of 10. So each of the 60,000 images has been seen once by the thing, okay? And okay, so that's that, all right? We can kind of take a look at, say, part of our weight matrix, okay? Okay, and these are the weights that have been chosen. I have no idea. Okay, again, we have when you're doing what do you call it, neural networks, the weights and how much these nodes are worth and the weights, those are a mystery. But what we're going to do is let's just go ahead and see how it performs. Okay, so I'm going to take the test data. So this is data that was not used in the training. Okay, I'm going to take the test data, which I've called XT. That's not the best name, but we're going to take 10,000 rows in our test data, and I'm going to go ahead and run it through forward feed. So we're going to take our X test data, multiply it by our current weight matrix, W1, which is the result after it's trained. So we've trained it, which means we've figured out what W1 and W2 should be. And so we're going to take our trained W1 matrix to get our Z2s. We're going to apply the sigmoid function to Z2 to get A2. We'll take our trained W2 matrix, multiply by that, and we're going to apply the sigmoid function to get our Y hats, okay? So let's just go ahead and take a look at like the first 3 rows. Whoops. First 3 rows of Y hat, okay? And so we're getting, and this is hard to read. Round this off to like 3 decimal places. Okay, so we're getting stuff that I think we want to see. So after training, this first row is mostly zeros. There is a 1 right here that corresponds to digit 7. The 0 is over here. Here we got mostly zeros. These are pretty close to 0. We got 0.057. And this is not quite 1, but it's 0.886. So we would say, okay, this should be a 2. And then this third row, it's a 0. These are all zeros, and this here is a 1. Okay, so this would probably be a prediction 1. Okay, and so we're going to take this, and I'm going to turn this into a guess. But and the way I'm going to do this is I'm going to take the column that's the biggest. I'm going to say max column in Y hat minus 1 will be our guesses. So if I take a look at the guesses for the kind of the first 3 values, it says it's a 7. Okay, that's this column. This is a 7, and this is going to be a 2, and this is going to be a 1. Okay. All right, and what we can do is we can go through and we can say, well, is it really? Let's see how our predictions did, right? So this first one we're hoping looks like a 7. Oops, not training. Let's do show digit. We're going to do our test data, and we'll look at the first one. It should be 7. Okay. Oh yeah, that looks like a 7. Good job. Okay. And let's look at the second one. The second one should be a 2. 2. It should be a 1. Okay. So let's do Uh, okay, guess 1 is a 7, and it's indeed a 7. Guess 2 is a 2, and yep, that looks like a 2. And guess 3 was a 1, and yep, that looks like a 1 to me. Okay, so so we've tested this out just for a few things, and man, we are not in class, so I can't see you guys, but this is impressive, right? um, we're giving it images, okay? We're giving it these little 28 by 28 images, and it's correctly guessing, okay? And I'm not using any kind of I'm not using any fancy packages here. This is all just some matrix multiplication, calculating the gradients. Yeah, this was a little bit of a pain to do on Monday, but we figured out what matrix operation to do here, and it's done that. Okay, Trevor asks, is this looking for pattern in the neurons or the number of activated ones? All it is doing, literally, all it is doing is just taking the x, multiplying by a matrix, and we apply the sigmoid function to that product, and then it multiplies those values by another matrix, and it applies the sigmoid function. That's all it's doing. Okay, there's nothing, there's no like, all of these things. This is just matrix times a matrix, apply a function. Matrix times matrix, apply a function, and that is producing our values. The thing was, what values do I use in these weight 1 and weight 2 matrices? Okay, and it's the what's basically happening is, if you correctly choose the weights to go into weight 1 and correctly choose the weights to go into weight 2, just taking these two things, yeah, will work like magic, in that you just take the x, you multiply it by a weight, apply the function, multiply it by a weight, apply a function, and you're going to be able to get predictions, right? And so, you know, I mean, we can keep going through this, and we can kind of just say like, all right, let's see the next image. It's guessing a 0, and what does it look like if I oops, if I graph that? And yeah, that looks like a 0. Okay. All right, and so what I'm going to do is I'm going to say, all right, let's go ahead and take all of the guesses and let's compare it to all of the results. Okay, and basically I'm going to create a table of the results versus the predictions. Okay, and this is what we call a confusion matrix. Okay, so this the way I have it set up is, you know what, let's make this bigger. All right, so we're going to say guess equals guess, and actual equals this, and let's table that. Okay, so my guess, when I guessed 0, okay, the actual value, maybe I should flip this around. Okay, so when the actual value is 0, I guessed 0 941 times, but I also incorrectly guessed it 2 10 times, and a 6 21 times. And we can understand, like, if the actual value is 0 and it turned out that this was a 6 or something, or I guessed a 6, we would forgive that, right? Okay. When the actual value was a 1, we guessed 1 1100, you know, this many times, and I made some mistakes a few times. Okay, not I, the guessing system did. Okay, and so most of the things are on the diagonal, indicating that we got things correct most of the time. But sometimes we got it wrong. Like when the actual value was a 3, we incorrectly guessed a 7 and an 8 a few times and things like that. So so we can kind of get kind of a, you know, how well is our prediction by taking all of the values that are on the diagonal divided by how many things we tested, and we're getting around 92, 93% accuracy. Okay, 92 or 93% accuracy. So and then we can just kind of see, well, how did it perform on some of the training data, and things like that. We can look at which of these were mistakes. Okay, so we can say, all right, so these are some of the mistakes, and so we can look through and we can say, okay, so for this one, the true answer is 3, and this is a 3, but when we pipe it through, it guesses a 2. Okay, so it makes mistakes. Okay, the true answer here is a 5, and it's guessing a 3. Okay, and so it's not perfect. Okay, but it is interesting that just with the way we've set up the matrix, or set up our system, is just taking that input of 784 values, okay, and it just multiplies it by these different weight matrices, and it runs that. Okay, does running more gradient descent make it more accurate? Okay, so there's a possibility. Yeah, you can run it a few more times, do more iterations, and it might improve the accuracy. I doubt it will improve it that much. Okay, so after 6,000 iterations, I don't know quite the landscape of the loss contours and stuff, but we've probably reached a fairly flattish region in our in the gradient descent. Okay, we're probably not going to get a ton of improvement. I mean, we might come across some kind of thing, but probably to increase accuracy, we'd probably need to tinker with the architecture of the network itself, maybe add another hidden layer, maybe add a few more nodes. And this is kind of an active area of research, because right now, as far as how should you design your neural network, people don't have good answers. Okay, it just says like, hey, let's try this out and see how it works out. And but there's not a whole lot of if you watch videos on neural networks, most of it will say if they're honest, a lot of the authors, the people will say, I've arbitrarily chosen how many hidden layers to have. I've arbitrarily chosen how many nodes to have in the hidden layer. And people will have different rates of success. There's other designs. So what we've been doing is kind of the simplest, where each node is connected to, each node in this layer is connected to every single node in the next layer. That's what we call a fully connected neural network. But there are designs where not every node is connected to the next one. There are designs where you will group some of the nodes together and kind of collapse them into a single value. There's all sorts of stuff. You can take an entire course and spend your entire career dedicated to developing and improving neural networks. This is about all we're going to say on neural networks. Starting next week, we're going to change topics and do something else. But I thought it was kind of it's a very neat subject, and it fits in well with kind of the theme of computation, optimization, and working with matrices. So I slipped it into our class. This is not a standard topic. This is not one of the required topics in 102B as far as mandated by the course description, but I thought it was pretty neat. I hope you guys enjoyed kind of seeing this, and you can kind of play around with this a little bit, and you've got a little bit of neural network stuff in your homework, where you'll be predicting what is it, subspecies of the iris data set, which is kind of the classic machine learning data set as well. I don't know, did you guys have any more questions here? Oh, the second quiz answer. The second quiz answer is B. B as in bear. No? Okay, well, that's all I have for you guys today. So I hope you guys enjoyed that and think it's kind of neat. And again, sometimes we use these packages in R that do stuff, and there certainly is a neural network package in R that can set up and train neural networks. But I think there's something a little bit fun and rewarding about building something pretty cool out of just simple matrix operations, right? Matrix operations that we kind of went through and explained. And it's neat that just something as simple as that can go through and start making predictions for images. Okay. All right. We'll go ahead and we'll stop.